In this tutorial, we're going to build a guardrail for an AI model using ZK. And what does this mean and why is this important? So this is important because, as you may have known, there are many AI agents interacting on chain, posting on Twitter, buying, selling tokens, tipping users, but there is one big problem, is that us as users, we can't verify, we can't know what was actually thought and produced by the AI and what was thought and produced by the creator, because every creator of AI models at this point in time has a backdoor, and that backdoor can basically inject or tamper the AI model without us being able to verify it. But this can be solved with zero knowledge. With zero knowledge, we can produce proofs, verifiable, then basically that don't allow the creator to inject something, removing this backdoor existing right now. We're going to use the ZKML library. That is a library that makes it very easy and convenient for us developers to start creating ZK proofs for AI models, and we're going to be deploying on Scroll. It's a layer 2, a ZK EVM, which is a perfect place for us developers to make cheaper, and also Scroll has been pioneering the ZK compatibility on ZK DSLs, so it's very possible and it's a perfect place for us developers deploying zero knowledge applications. So we're going to build using this collab that the ZKML library provides already. And before going there, I want to show you this cool project using ZKML, which is a crypto idol that basically she will hear you singing, you will sing for her, and she will mint an NFT depending on the way you sing, depending if you are angry or you're singing sad, depending on how you make her feel. It will mint an NFT for you, which I think is very cool. But of course, many more things can be done with AI. This is a totally new area of exploration on what type or what capabilities under what data the AI model will be deciding things. Okay, so on this Google Colab, we're going to do a couple of changes. What we're going to be building right now is a model, very simple model here using PyTorch that is going to decide on a tip recipient. So the AI is going to decide to tip a user, and we're going to give him 1,000 tokens on chain, but only if we can produce a verifiable ZK proof that the AI actually decided to tip that user. The way based on what data, all the training on that model will not be covered in this video. We'll just make it super simple with this model that we're going to train here, that is just going to tip a specific user. Going to tip this specific user, and by the way, this is going to be on the description. This tutorial, like this article, is going to be linked on the description, and also by the end of the tutorial, we are recommending you the Kaggle Intro to Machine Learning. So if you're coming from blockchain and you want to learn more about machine learning, we recommend this. And if you're coming from AI, I will recommend you the Level Up ZK content that will also leave a link here. More on that later on this video about what specific knowledge of ZK do you need. Okay, so let's copy this, and we're going to replace the first one with this. And by the way, by the time that you watch this video, it's going to be fixed, but I forgot to import the OS library here. Okay, so now run this, and as I mentioned before, this is going to train a model to basically just tip this specific user. That is a wallet that I control, but yeah, you can just change it with your address, and better yet, imagine different ways of pulling data and creating very interesting models to do very cool things on chain. So next, we're just going to one by one execute all the initializations that ZKML requires, and we're going to produce basically a ZKML model that is verifiable, and then a secret circuit that, by the way, this is using Halo 2, which is very impressive. It's a very good tool, and the first version on Scroll, the current live version on Scroll, uses also Halo 2, and yeah, this is very, very, very cool. But we as developers, if that's abstract from us, we can just interact with all the libraries that ZKML already provide for us. Okay, so next step is going to just add this snippet, and what this is going to do, as you can see here, this produced a CK proof before, but now we're going to produce a smart contract that is able to verify the proof. This is very interesting. As you can see here, if you copy this and you go to Remix, we're going to create a new contract. I'm going to call it Verifier, and what this produces, as you can see, is a fully working Solidity code. And yeah, this has the verify proof function, where you will be able to send a proof and it will return true if the proof is valid. And on top of this, you can add whatever logic you want. In our case, we're going to add on top of this the logic of sending tip, making an ERC to the transaction. But there's also a lot of things that you can do, a lot of things that you can experiment to. Okay, but let's take it one step at a time. Let's now deploy this. And as you can see, if you're not able to deploy this, you have to enable optimizations, because if not, it's going to make this error, because as you can see, this is a very big and chunky contract. So you have to enable optimizations, and once you have done that, you will be able to select here injected provider MetaMask. As you can see, this I'm using a Scroll, but also you can deploy this on any EVM chain, Ethereum layer 1, optimistic rollups, any other alternative layer 1's EVM. But when it comes to CK EVMs, I haven't tested on the other ones, but it's very hard for a CK EVM to support this, because some specific precompiles, but Scroll supports it, so it's good. We should be able to deploy on Scroll. And yeah, so okay, so my remix got stuck. So I'm going to, sorry about this. Okay, it revived. Okay, no worries. Okay, so this should be deployed on Scroll now. Here it is, and this is the verifier contract. Okay, so let's continue with the tutorial. The next step is to generate a CK proof. We already, as you can see, we already generated one here, but I recommend you to generate one using this code that I'm providing here, because this is going to produce it in a way that Remix expected, that Web3.js and Ether.js expected. This is a big hash, a big hex that, yeah, where the proof is produced. Okay, next we're going to oh, by the way, you can let's try this. So basically here, when you will be able to just send it like this, and yeah, basically it will return. You will be able to send a proof to this Halo 2 contract, and it will return true if the proof is valid. Okay, I don't know if my remix or my internet connection is a little bit slow, but okay, yeah, it's not encoded correctly, because it's expecting it in a different format, and yeah, don't worry about it. We're just going to do it later when we interact with the tipper contract. That will make a lot more sense, so please be patient there. Okay, next we're going to launch the token. So the token is just an it's very simple Open Zeppelin generated wizard token that's going to mint 21 million token for me. So let's also deploy this token. Okay. I think I may need to. Okay, now here you go. Maybe I deployed 2 by accident, so I will just cancel 1. Okay, so I deployed the token now. Okay, so it's deployed. Here is my token. Let's add it to MetaMask. Let's add it here. I'm a bit lost because the new MetaMask interface. It is new, right? And I'm a little bit confused here. Okay, but here is this is my new token. These are other tests that I did before, and I'm going to reject this because I launched the token by accident 2 times. Okay, so I now have the token, I have the verifier. The final piece is the tipper contract, and this is the most important one. So let's take a little bit of a deeper look. I'm going to call the tipper. So here, first, let's change the verifier contract by the one that you just deployed, and the token contract by also the one that you just deployed, and let's compile it. And while we deploy the tipper contract, remember to choose it from here. We deploy it. Let's take a look at how does it works. So the main function, the only public function, is the verify and send tip. So usually these type of functions will make 2 things. First, verify a proof, and then add the custom logic that you want. So in the first part, we use the verifier Halo 2 contract that we just deployed before this one, and if the proof is not valid, we're going to revert. But if the proof, as you can see, is going to revert. But if the proof is valid, you can add whatever logic you want. For example, mint an NFT, make a swap in Uniswap, and do whatever you want. But only if the proof is valid. And in this case, because we're building a tipper AI agent, we're going to transfer 1,000 tokens to that specific user. And one very important thing is that all the parameters have to be returned by the AI. And once the AI return, we have to decode it, grab them from the proof. They have to be baked in the proof. And this is important because one, we want the actual AI to decide on the parameters on what we're going to execute. In this case is who is going to receive the address of the recipient of the tip. As a refresher, remember here in the first one we train the AI model so it will send tips to this specific user. You can change it to your own address, so you can receive the tip yourself, so you can test it out. But it's very important that whatever for example, if the AI decides to buy a token and will return the token address, for example, and it's very important that it's the proof inside the proof is baked the address, because if you add it as a parameter, someone can impersonate it or someone can front run you. But if it's baked on the proof, no one can tamper it. So that's why I added this function down here that extracts the address, because it's encoded in a very specific way that ZKML requires you to encode it, because basically you can just fit an address on a parameter from ZKML, but you will have to encode and do a little bit of encoding and decoding. So this is how I did it myself. And yeah, just basically the proof and the public input, in this case the public input is the result of the proof or result of the AI computation, will be encoded in bytes. Then I group them and I return it. So yeah, I would just want to stress that it's very important that everything is baked on the proof. Okay, so let's just try it out. let's first send 1000 token to the tipper contract, because if it doesn't have the token, he won't be able to tip you, right? So let's send to this address 1000 tokens. Let's see here, 1000 tokens, and after that we will be able to send the proof here. Let's see how let's send the proof the way that it expects it. So this is why I added this other like way of generating the proof. So let's see, let's wait for the tokens to arrive to the contract. Oops, something went wrong. Let me try again. Yeah, I don't know if it's my internet connection or something wrong with my RPC. But yeah, let's try that again. Okay, let's send 1000 tokens. Let's see if this time everything is correct. And also we will be able to see everything on Sepolia scroll scan. So let's inspect it here. Okay, so this is the tipper contract, right? Okay, so okay, the 1000 token arrived this time. Oh, good. And now we're going to send the proof here, and when the proof arrives, if it's correct, the 1000 tokens will be sent by the recipient on the proof by decoding the address from the proof and reconstructing it and send it as a parameter. Okay, and let's confirm this transaction. And a couple of important things to mention on the ZK side is that, okay, so let's see if this worked. Okay, so 1000 token out for this specific address. That is the one that we trained the model to do it. Okay, so a couple of important things about ZK to mention here is that you need to, depending on the project that you are doing, you will need to gather some specific knowledge about it. So, for example, if you resubmit the proof, if the contract has, for example, 10,000 tokens, and you submit the same proof 10 times in a row, of course, the contract will give 10 times the tips, and you can train the contract basically. That will be a problem. So there are a couple of specific knowledge about ZK that you need to know. For example, this can be solved with nullifiers, so one transaction can be re-executed. Also, you can have some privacy features. As you may have seen right now, there's no privacy here, which is okay. We're using just, remember that ZK has two important features. One is privacy and the other one is scalability. We're just using scalability here because we need ZK to make it cheaper to verify the computation to generate the computation of a model. Because if we bake everything on the contract, it would be too expensive, but with ZK it's way cheaper. But if you can add also privacy features to this and experiment with that, and yeah, what I'm going to this is that we also have here in Level Up. So so subscribe also to this Level Up channel and also to my personal channel, Filosofía Código. I have a channel in Spanish and also in English. And here, also on Level Up, we have a lot of content and about ZK here that you can get you started, so you can combine everything about ZK, combine with your knowledge with AI training. And this is like a perfect combination that has a lot of potential, and this is just getting started. That's why we decided to do this video. So yeah, let us know if you have any good ideas, either in the comments or in Twitter. Yeah, thanks for watching and happy hacking. Bye. Also, if you have any question, leave it in the comments, any comments. So yeah, bye.